In this video, we're going to practice some related rates problems. Let's suppose that x is a variable and x changes with time. Okay, so x changes with time t, and the rate at which x changes is dx dt, the derivative. That's the rate at which x changes. Because the derivative always gives information about how quickly a variable is changing. So if the variable changes, if the variable is related to time, then how quickly the variable changes is its rate. Now let's suppose we have another variable y, and let's say y also changes with time. And let's suppose x and y are related to one another. Let's suppose that y is equal to 2x. So they're related by this little equation. So if these variables are related, then their rates are also related. And we get the relationship between the rates by differentiating with respect to time. So on the left, that would just be dy dt. And on the right, that would be 2 dx dt. So these are related rates. In many of the related rate problems that we come across, the variables that are changing with time are variables in either a volume formula or an area of some geometric object. So suppose we have a spherical balloon, so we're talking about a sphere, that's increasing in size, so its dimensions are changing with time. The volume of a sphere is given by this formula, volume equal 4/3 pi r cubed. So so in that way, v is related to r in this equation. So now we want to find an equation that relates dv dt and dr dt. So we're going to differentiate with respect to t to find that equation. So we're just going to differentiate with respect to t. In all related rate problems, we differentiate with respect to t, where t represents time. So on the left we have dv dt. On the right we have 4/3 pi. And here we're going to be doing a little chain rule, bring down the 3, r squared. And then here's the chain rule, we have to multiply by the derivative of r, dr dt. Pops out over there. We can just simplify by crossing out those 3's, and we have dv dt is equal to 4 pi r squared dr dt. If we just examine this equation for a minute, we see that as the radius gets larger, dv dt gets much larger. Okay, so that's because of this r squared over here. So for radius, let's say, if we compare dv dt for radius 10 and for radius 100, it'll be much larger for radius 100 because of this r squared factor right here. Okay, so here's our first related rate problem. This says that air is pumped into a spherical balloon at the rate of 100 cubic inches per minute. All right, we're going to be using the volume of a sphere. That's the equation that we'll be differentiating. And we want to find dr dt when r is equal to 5. That's part A. Okay, so what are we given? We have to understand what we're given. This 100 represents how much air is pumped into the balloon. So that's how quickly the volume is changing. So you see the word rate over here tells us that we're talking about a rate which would be a derivative of one of the variables. In this case, the 100 cubic inches refers to rate that the volume is changing. So that would be that 100, that's dV dt. Now we want to find dr dt. So it would be nice if we had an equation containing dV dt and dr dt. So we're going to get that equation by just differentiating. So our first step here will be differentiate. And here we're told first we'll differentiate and then we'll substitute in the given values like the 100 and the 5. So first let's differentiate v like we did in the previous example, and we get dV dt is equal to 4/3 pi times 3r squared dr dt. And just like before, we'll cross off these r's, and we have 4 pi r squared dr dt. And now for part A, we want to find dr dt when r is equal to 5. So now we're going to substitute our values in order to figure out what dr dt is. So for dV dt we put 100. For part A, we want to figure out what dr dt is when r is equal to 5. So we're going to substitute in 5 right here, right over here. And now the only thing that's left is dr dt, so we're just going to solve for that. All right, so we have 100 is equal to 4 pi times 25 dr dt. Okay, so we have, this is 100 pi over here, so dr dt is equal to 100 divided by 100 pi, and that is 1 over pi. One over pi, and r is one-dimensional, the radius is one-dimensional, so that would be inches per minute. Okay, now part B, we're going to again substitute, but this time we want to figure out dr dt when r is equal to 20. So we're going to substitute r equal 20 this time. Okay, so this time we're substituting r equal 20. Again, we're up to the substitution step. We're substituting right into here. dV dt is 100 equal 4 pi 20 squared dr dt, and we're just going to solve for dr dt. So there we have 4 pi 400 dr dt. Okay. All right, so that is 1600 dr dt. So we're going to just divide both sides by 1600 pi, and that will be dr dt. Just simplify that, and we have 1 over 16 pi, and again the units would be inches per minute. So if we compare both results, we see that if the volume is increasing at a constant rate, then the rate of change of the radius is basically slowing down. When r is equal to 5, the rate was 1 over pi. And when r is equal to 20, the rate is 1 over 16 pi, which is much less. In this exercise, we're just going to practice working with an equation that involves 3 variables. So here we have y, x, and z. And we also have a side relationship, z is equal to 3x. So in part A, we're asked to find an equation that relates dy dt and dx dt. So we want to first eliminate the variable that we're not interested in, and that would be z, because z is not mentioned here. So in part A, we'll have an eliminate step that we didn't have before, and we have that step that's always our first step, in fact, when we have three variables. Okay, so we'll eliminate, and in this case we're going to eliminate z. Okay, so we're going to eliminate z here. So we'll start with y equal 5 x squared z, and we'll replace z with 3x. So we have y is equal to 5x squared times 3x, or y is equal to 15 x cubed. And now we want to relate dy dt and dx dt. We only have y and x in here, so just differentiate with respect to t. So the next step is the differentiating step. And we have dy dt is equal to 45, bring down the 3, 45 x squared dx dt. And that's as far as we're going here. Okay, in part B, we're going to eliminate again. This time we want an equation relating dy dt and dz dt, so this time we're not interested in x, so we're going to eliminate x in this step. Alright, so we have y is equal to 5x squared z, and we know z is equal to 3x. Let's solve for x. That means x is equal to z over 3. So we solve for x so we can eliminate it. So right over here we're going to put z over 3. Alright, so we have y is equal to 5 z over 3 squared z. That's 5 z squared over 9 times z. Okay, so that's y is equal to 5/9 z cubed. So here we have an equation relating y and z. So now we're ready to find an equation relating dy dt and dz dt, and that would be obtained by differentiating. So let's do that. And so here we have dy dt is equal to, and just bring down the 3. 3 times 5 is 15. So that would be 15 over 9 z squared times dz dt. Okay, so that's what we were asked to find. All right, and just to reiterate, the main point of this problem is that we first eliminate before we differentiate.